Okay, now we're ready to move on to parallel circuits. So we're going to go back to an RL circuit. What happens if we have a resistor and an inductor, a coil, connected in two parallel branches in our AC circuit? First, I would say it's the same but different. Okay, we have to, it's different initially because we have to make a couple of choices and decisions and get the right things in the right place. But once we get started, it becomes the very same process that we've already done in our series circuits. So, what do we have to latch on to initially to use our anchor to make our decisions? So what was it we said about a series circuit that we used to build our triangles? We said in a series circuit, it's the current that's constant. No matter where you take the measurement in the circuit, you'll measure the same current. What's constant in a parallel circuit? It's the voltage, right? The parallel circuit, each parallel branch will see the same voltage as the power supply. So the first point to make is that in a parallel circuit, voltage is constant. Okay, so that is our first piece of information that we're going to use to figure all of this out. So that means now it's going to be our voltage vector that we're going to place at 0 degrees. So instead of 3 current vectors at 0 degrees to build our 3 triangles, it's going to be 3 voltage vectors that are going to be at 0 degrees. And in a series circuit, because the current was constant, our 3 triangles were impedance, voltage, and power. Now that our voltage is going to be our reference point at 0 degrees, which is constant, our 3 triangles are going to be impedance, current, and power. So let's look at current here for a second. Current. So if this is voltage at 0 degrees, here's the next piece of information we have to adjust. What did we say in... Well, actually, we don't need to adjust. It's just going to look different. Okay, the rule is the same. In an inductive circuit, what can we say about the relationship between voltage and current? Well, this is where we go back to Eli the Iceman. Eli the Iceman. And so is it a capacitive circuit? No, it's not. We're looking at an inductor. So in an inductive circuit, the voltage leads the current, or the current lags the voltage. And so now it's the voltage vector we've placed at 0 degrees. Where are we going to find the current vector if it's lagging? The current vector is going to be down there, right? There's the relationship between voltage and current. Okay? Now, I'm going to erase this because that's not how we do this when we get into our vector addition, right? If we want to build a triangle that represents current, then we know that here in the resistive branch of the circuit, our current is going to be in phase with the voltage. And so this is I subscript R, the current through the resistor at 0 degrees in phase with the voltage. And then we said the current is going to lag the voltage. So here it is down here. There's our current vector. So this is I through L. And so finally, the hypotenuse, IT, I total. Okay, so there's our couple of adjustments. The voltage is constant, so it's now our reference point at 0 degrees. Okay, and that's really all. Now, what the result is that it flips our triangle. It looks like it's upside down, right? Because remember when we built our series RL circuit triangle, it was up here in what would be quadrant 1. Now we're down here in quadrant 4. Okay, so it appears as though we have flipped the triangle upside down. And the reason for that is we're building our triangle off of a different vector. Okay, we're no longer putting our current vector at 0 degrees. We're putting our voltage vector at 0 degrees. So it didn't really flip upside down. It just moved backwards. Okay, so we could draw this anywhere, right? We could draw our voltage vector there and our current vector there. Okay, and I don't know what angles those are, but it represents the current lagging the voltage by 90 degrees. We can put them anywhere. Okay, in the series circuit they sat here. In the parallel circuit we have just slid them back 90 degrees so they sit there. Okay, that's the adjustment. And that's pretty much it, although there's one more thing that you've got to watch out for, and this gets nasty. Okay, that's the current triangle. That's going to be our power triangle. It's all good, but let's come back and do our impedance triangle. And here's what's nasty. There's E, but there's the vector that represents the resistance in our circuit. Our resistance in our parallel circuit. Reactance in our parallel circuit and total impedance of our parallel circuit. How do we calculate total resistance in a parallel circuit? We use the inverse equation, right? So the inverse of RT equals the inverse of R1 plus the inverse of R2, etc., etc. Okay, well, guess what? The inverse of the total impedance equals the inverse of the resistance plus the inverse of the reactance. Except don't ever write this equation down, okay? You just made a note of it, and now I want you to never use it again. Because this is a linear equation, right? And so we can't exactly use that. We have to consider our angular relationships, okay? But the logic holds firm. In fact, you know what? If you're pausing the video or whatever, I don't want you to be looking at that. So now that I've taught it, I feel the need to make it go away really, really fast. But the logic is true. If the total, so the inverse equation means, okay, remember, let's go back to DC for a second. Why did we need to use the inverse equation to calculate total resistance? Because the total resistance of the circuit will be less than any given path, right? We add another parallel branch, we're building another bridge across the river, we got more traffic flowing across the river, we're actually reducing the amount of resistance in the circuit as a whole. That's what the inverse equation does for us. Every time we add another parallel branch, the total resistance of the circuit gets smaller. And so this Z must be the smallest number in our collection of numbers. And yet it's the hypotenuse. And so how do we make what is the smallest number the biggest number? By doing that. And so the vector at 0 degrees in our impedance triangle represents not R, but the inverse of R. And the adjacent, the opposite in our triangle is not XL, it is the inverse of XL. Okay? So this is where things start to get messy really, really quick. Okay? I know some of you are going to struggle with this. Okay? It's just about practice. Go through the exercise sheets, work on it, but here's my piece of advice. I'll do another video, we'll do some actual math. We'll put some numbers in here. But here's my advice, is don't try to solve the triangle here. Okay? Just get away from this impedance triangle as fast as you can. Solve the triangles over here, and then just use Ohm's law to come back and fill in the value of R. So remember, once you know E and once you know I, you use Ohm's law to find R. That is R, just like it always has been. Ohm's law will not change. It's not the inverse of R. Okay, the inverse of R is a value that you only need to use if you are trying to solve this triangle. And so if you can avoid solving this triangle, you never actually have to deal with the inverse values. Okay? Ohm's law will always give you the value of the variable, not the inverse of the variable. Okay? So that's the lesson. I'm going to stop the video there. Next video we'll be applying some math to this. We'll try to solve a parallel RLC circuit together.